Did you hear about the statistician who took the Dale Carnegie Secrets of Success course? He improved his confidence level from 0.95 to 0.99. And today we're going to be talking about confidence levels and confidence intervals. So we're doing part one here, which is how to state what you're going to do and your initial plan when establishing a confidence interval. So when we take a sample or a survey, what are we trying to predict? We want to know what really is true. For example, in our bead activity, we were trying to predict the percent of beads that are black. So we're trying to predict the parameter, what holds for the whole population, not just for the sample or samples that we took, but for the entire group. All right, so it's for the entire population. So when we're doing a confidence interval to predict this parameter for our population, our first step is to state the parameter you want to estimate. In our bead activity, our parameter that we were trying to estimate was the true proportion of black beads in the bin. Now, because we don't actually know P, the parameter, we're going to use a value called P hat, which is our point estimate, which we get from our sample. All right, so P hat comes from our sample because we're not going to count all the beads, and this is our estimate. Now, if we got 53% of our sample is red, does that mean 53% of our population has that measured characteristic? Well, no, because we know there's randomness and because of sampling error, if we did another sample, we're probably going to get a different value. Now, when we make a prediction using our sample, we know the true value could be lower or it could be higher. And that, again, is due to sampling error. The goal of the confidence interval is to account for the size of the sampling error. So if the true value or the value we get is here, we're like, oh, maybe the parameter's down here or maybe it's up here. So actually down here probably for you and up here for you. So confidence interval is to set a window where we think the true parameter could be with a certain amount of confidence, and we'll get into that later. After you determine what parameter or state the parameter you're trying to estimate, you need to have a plan. So one step is to identify the method that you're going to use. We are currently learning our very first method, and I'll give you the name in a second. But before we can use this method, we have to check the conditions to make sure that we can. So when we sampled the beads in our class activity, we used a histogram, right, to estimate the confidence interval. So we could say, oh, okay, our histogram goes from here to here, so that's probably where our proportion is. And that's a good way to do it. Now, one thing we did learn earlier is that the sampling distributions for proportions could be approximated with a normal distribution. I've told you before, the normal distribution's not going away. We use it a lot. Now, the only way we can use a normal distribution or an approximation is if three conditions are met. And I'm going to go over those in just a sec. But let me go ahead and first give you the name of the method we're using. It's called a one sample Z interval for P. And if you look at it on your calculator, it's one prop Z int. So let's go to these three conditions. You've already learned them, but I'm going to review them. First of all, there's the random condition. And that's basically that you need to know that your data either comes from a random sample or you're told that it is representative. If they say it's representative, you're fine, because that's the whole point of taking a random sample is to have a representative sample. Now, the 10% condition, that comes into play when we sample without replacement, and that's most of the time. Normally, we pull our sample out, we look at it, and we measure it, and then we're done, and then we put it back in, right? Now, putting it back in doesn't count for replacement because the sample is just that one-time takeout. I didn't like pull one bead at a time 20 times and put them back in. I pulled out 20 beads at once or 100 beads at once and looked at that sample. All right, so when I am doing things like that, which is most of the time, the sample size needs to be less than 10% of the population. And then you can verify that it's less than 10%. So if you know the population is 3,000, as long as your sample is less than 300, you're fine. Or if you take a sample 200, but they don't tell you the population, you can say, oh, it's just got to be more than 10 times my sample. Or if your sample is 200, needs to have a population of 2,000 or more. Now, the other one is the large counts condition, and you've heard me call this also the success failure condition. Basically, we need enough counts. The reason this is called large counts is we want to make sure our peak doesn't go off the edge of our histogram. You know how, remember how when we had NP less than 10, it chopped off part of the curve. So we want to make sure that NP is greater than or equal to 10, and that NQ, Q is 1 minus P hat, and remember I'm using P hat because I don't know P, that's greater than or equal to 10. Be sure you show the calculations. If you write condition names with just a check mark, that does not count as checking conditions, and you will be dinged, both on my test and on the AP test.